So let's look at this motor effect and generator effect as applied to motors and generators. So these are my bar magnets, if you like. I've got a whole bunch of them somewhere. You don't have to do it this way. Should I do it this way? Yeah, I'll do it this way first. So we just got a magnet. That's north, that's south. Got a wire running through it. We'll do a wire in red like we did before. Now, motor effect, we said we need a current flowing through it. So if I put my current going that way, the question we're asking ourselves is, which way will the force be? So our field is down, north to south. Our current is that way. Our force is going to be in the direction that way. Remember, when we're dealing with current, it's like we're pretending that there's a whole bunch of positive charges going from positive to negative. And so it actually does give us the correct direction of the force, because the rule's designed that way. We used electrons, we use the back of our hand, and we'd still get the same direction. So don't feel bad about that, because the electrons are going that way, and we use the back of our hand. So this is it. This is what creates motors. A common way for me to draw them is like this. I put my south over here usually, and I put a loop in there, and my loop goes through there, through there. Hopefully that's understandable. We put a current up there, comes back that way, and you ask yourself, which way is it going to go? Which way is the motor going to rotate? So again, we go north to south. Current on the left hand side, it's going to go down on that side, and on this side, again, we use our hand north to south. We have to flick it around, it's going to go up. So looking from this end here, this motor is going to rotate anti-clockwise. We're looking from this direction. What you've got on each of these loops here is you've got a length, right? So you can do that whole F equals BIL thing, right? Now the F equals BIL thing is just saying how much force we're going to have here and how much force we're going to have here. But remember, motors don't just use one loop of wire, right? Motors don't just use one loop of wire. So you'd multiply it by the number of loops. And of course, you'd have double the force. F equals BI2L would give you one loop times the number of loops. So this is not just a force, it's a torque, because it rotates about a center of rotation. So we can actually work out the torque. So have a look at my little videos, torque equals Benny and voltage equals Borny. I call them the Swedish tennis players. And one of those will work out the torque on a motor, and one will work out the voltage in a generator. Things to consider with this at the moment is when is the force at its strongest? Well, right here we've got the current, and that means charges are flowing perpendicular to the magnetic field, right? Nice, you get a nice torque. What happens with these charges that are flowing in this part? Well, they're flowing in the direction of the magnetic field, so no force. Same with this one, same with this one. So you've got to do that right-hand rule for all the directions. If we now flick this little guy into the vertical direction, can we do that? Yeah, we can. So if we've got our magnets, and now our loop is pretty much vertical. It's sort of like vertical. It's sort of like vertical. Ask him, what does it do now? And what you'll notice is, although your current in this top loop is not passing in the direction of the magnetic field, but is still perpendicular to the field because the field goes that way, you got to ask which way is the force on that top loop. So if this is north and this is south, and that's the current of current, then we do our finger thing and we do our charge movement, and we end up with a force going down on the top loop and a force going up on the bottom loop. That does not produce a rotation. So there's no torque when the loop is vertical. So no torque when loop is vertical. Alright? So what you tend to have in real motors is they put a whole bunch of coils so that it keeps going dunk, 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 like that as it goes round. So it keeps getting that torque. Also, you can imagine after it's done, even with the horizontal, when it goes 180 degrees, the torque's going to go back the opposite way. So what you have on the ends here, normally, is something to change the direction of current every half a turn to keep it going in the same direction. This is how you make motors, and it used to be a level 2 thing, and it's dropped out of level 2 now. Don't know why. Let's have a look at the generator. I always do a similar diagram for the generator. It's like this. And this time what we've got, the same thing, a wire going inside a magnetic field. We're going to still do it horizontal like that. But this time, instead of us having a current flowing, we're just going to move it. We're going to rotate it. We could put this on a bike or something, or a windmill. And we're going to rotate it clockwise. Now, when we do that, we again use our right hand rule to determine which way current's going to flow. So north to south, on this loop we're looking at here, north to south, up. It's going to push the positive charges up here. So we're going to end up with a positive here. Positive at the top. So it goes negative, positive, and on this side we'll get a similar thing. They're not going to oppose each other. They're going to both make a current flow this way. So what's happening here is you've got a movement of a conductor in a magnetic field. The force, as we worked out before, not the force, well it is the force on the charges creates an electric potential in that length and in that length. And the direction we work out from the Lorentz force law using positive charges will give us the current, and that all came from B equals B L V, where that's velocity and that's voltage. So moving a conductor in a magnetic field produces a voltage, and this is what we call a generator, sometimes called an alternator. This is how we make our electrical power in nearly every situation where we've got a turbine or generator in the car with your alternator. So again, the questions are things like when do we get the most voltage? And you'll see that when the current is flowing here, the velocity is at 90 degrees to the magnetic field. So the voltage is at its greatest at this point. If we turn the coil vertical, right, then remember that this whole coil, we're rotating it clockwise from this direction. And so at the top, the electrons are moving in the direction of the field lines, so there's no voltage. Remember that when we're rotating this coil is rotating this direction when it's horizontal, but when it's vertical, it's rotating that direction, which means it's in the direction of the magnetic field. So in its vertical position, no voltage. Alright, now we can then go to the trouble of working out a formula as to how much voltage we get out of one of these guys. And there's another little video on that. Voltage equals Born, one of the Swedish tennis players. Alright, have a look at that video, and that one helps you determine how much voltage we're going to get out of this. But hopefully that's enough for you to understand how the generator works. Don't forget the hand rules: right hand, direction of the field, direction of the movement. Your palm gives you the positive. So again, when we were on this side, on this one, north to south, down, down is that way, the thumb is the direction down, and the palm gives you the positive, so the positive was on this end. Alright, I think that's enough for this video.